Assalamu alaikum everyone, and today we are going to talk about acid-base reactions and buffer solution. When a strong acid or base reacts with water, it completely ionizes, which is to say that if every molecule of acid transfers its acidic proton to a water molecule. Here, this is a strong acid, and if every molecule reacts to this completion, this makes things neat and tidy. But when weak acids and weak bases ionize, they partially ionize, and they establish an equilibrium with the ionized and unionized form. So let's go over some math. Ka is the acid ionization constant. This is derived just as our Kc in our equilibrium video, and in this way, Ka is a measure of how thoroughly an acid-base reaction proceeds in the following direction. A larger Ka means the products and a stronger acid. A smaller Ka means more reactants and a weaker acid. A larger Ka is a stronger acid and therefore a lower pH. We can also experimentally determine Ka. Determining the Ka for phenol, starting with 0.1 molar solution and with a pH of 5.43. Here, these are the values, and we can use an icebox as we know it, and we can use the pH to calculate the hydronium concentration. The hydronium concentration is 10 to the negative pH, which is 10 to the negative 5.3, which is 3.72 times 10 to the negative 6 molar. And the conjugate base and the conjugate acid has the same concentration as they are the same. And the initial change is pretty much negligible. So let's plug in the values. These two are the same, so we square and then we solve for the top and then we divide, and the final answer is 1.38 times 10 to the negative 10 Ka. By this way, we can also find the degree of ionization. Here, the degree of ionization is 3.72 times 10 to the negative 5. Degree of ionization is the ratio of ionized to unionized acids, or the percent ionization. This is a pretty weak acid, as only so few of it was donated to water. We can make ice boxes for weak acid, weak bases, and polyprotic acids as well. A buffer solution is a solution that resists change in the pH. Buffers are really important in chemistry. We buffer swimming pools so that it doesn't damage our human skin. I'm pretty sure you heard that swimming pools contain chemicals. Now you know why. We buffer soda pops so that there's no acid flavoring, because that can damage our teeth and tissues. And we even have pH in our blood, which helps keep its pH, otherwise it will lose its capacity to carry oxygen. Buffer solution chemically is a solution of weak acid plus its conjugate base, or a weak base plus its conjugate acid. These are called acid-base pairs. Weak acids and bases partially dissociate. It's their weakness that makes them great buffers. Since they don't fully dissociate in water, the undissociated buffer can act as a source for protons, which helps neutralize a strong acid or base being added to a solution. It's really all about equilibrium. Now, say in this reaction we have 1 molar of acetic acid. To make a buffer, we need to increase the concentration of acetic acid by, say, adding sodium acetate to it, because it dissociates completely, making tons of acetate ions. Now let's add enough of the salt to make a 1 molar solution. So we know how much acid and how much acetate there are. But the important thing is the pH, and to determine that we need to know how many protons there are. Don't worry, an icebox will take care of everything and will help us keep track of everything. Now here we don't include the sodium. Sodium is there and will remain, but it's just a spectator ion. It won't take part in the main reaction. And these are the values, and the Ka is 1.76 times 10 to the negative 5. Now plug that in and solve for the concentration of protons, and by doing this we can use some algebra and simplify it. That doesn't look anything simple. It's all quadratic, and unless you have the time to watch all of my videos on the quadratic formula in my algebra series, I think I should tell you another tactic. You see, acetic acid is a pretty weak acid, so the X value must be really small. Now, if it's so small that after rounding up to significant digits, it doesn't change, then just ignore them. Now, this X here plays an important role in the equation, so we won't ignore it. But the rest, let's just ignore it. The factors will cancel out, and the X value is 1.76 times 10 to the negative 5, which is the concentration of protons, and the pH will be 4.754. Now we know the pH, so let's resist. That's the whole point. You see, hydrochloric acid, while exposed to water, dissociates completely, but partially in acetic acid. Protons will join up, and we can do one thing, is take some amount of concentration from the acetate and add some concentration of acetic acid, and then plug them into the hydrogen concentration, and the answer is 1.80 times 10 to the negative 5 molar. The pH is 4.7546, which is almost the same as the previous pH. Actually, if you round it up into only 2 decimal digits, then they are pretty much the same. So with that, we have a very good idea of what buffers are and what acid-base reactions are. So that's all there is to it. Thank you for watching. If you have more friends who are confused in this similar subject, make sure to share it to them, and please like the video and subscribe for more videos about math and science. And thank you for watching, and I will see you next time. Bye.